We got one more page here that gives us a real-world problem. I can solve real-world problems using complex numbers, and it talks about electrical engineering. So let's read this. Electrical engineers use complex numbers when analyzing electrical circuits. And electrical circuits can contain three types of components: resistors, inductors, capacitors. As shown in the table, each type has a different symbol in a circuit diagram. Each is represented by a different type of complex number, that's important, based on the phase angle the current is passing through. So here we go. We can see that a resistor is represented by that right there, that symbol. So this must be the resistor. I'm going to put an R down here, and it's going to be a real number, so just 4. We can see that an inductor, phase angle 90, is an imaginary number. It's represented by this. So I'm going to say I for inductor, and it's imaginary number, so let's say 3I. It says larger than 0, right? And a capacitor represented by this symbol, so right down here, negative 90 is imaginary number, where B is less than. So this is negative 3I, and that is going to be our capacitor. So let's keep going. The total impedance is the sum of the impedances of the parts. Well, we listed the resistor of 4, right? We listed the inductor as 3I and the capacitor as negative 5I. So the sum is going to be 4 plus 3I plus negative 5I, which should give us a sum of impedance of 4 minus 2I. I'm gonna circle that right there. All right, that's the sum of the impedance. Now we got Ohm's law for electric circuits. It says that the voltage V is measured in volts. All right, the product of the current I, right, measured in amps, and the impedance, that's what we've already done. So these numbers up here are our impedance. Z is our impedance, which is weird because I starts with the same letter as impedance. And we get it by multiplying I times Z. Alright, so that tells us once again that voltage is the product of the current and the impedance. Okay, and then it tells us our current. So our current is 24 plus 12I. So let's go down here and we'll do this. So to get our voltage, we take our impedance for the resistor, which is 4, and multiply it by 24 plus 12I. That is voltage times impedance right there. If I go through, what is that? 96 plus 8I. Let's underline that. The inductor, so our inductor was 3I times the same thing, 24 plus, ooh, that should have been a 12I, huh? I didn't do a 12I. I did a 2I. Let's put a 12I there and adjust this to 48I. 48I. Alright, so this is 24 plus 12I, and if we multiply that, well, 3I and 24I. Well, let's do this 36I right here. So that's going to be 36I squared plus 12, 6, 72I, right? Which we know that 36, or we could say, since that I squared is negative 1, negative 36 plus 72I. There we go. Alright, and the capacitor we know is negative 5I times 24 plus 12I. So I'm going to do this I part first because it looks like it's going to turn real. That's going to be negative, right? This is negative 5I times 12, so that's negative 60I squared. Remember, I squared is negative, so it's going to turn into a positive 60. And negative 5I times 12 is, or times 24 is going to be negative 120I. Negative 120I. Which I'm going to put over here. Negative 120I. And this last part's going to ask for the sum. So I'm going to bring that 96 right here. 96 I'm going to bring the 48i over here, and we're going to get the sum. Well, if you add all this up, that's up here, that's 120, and that's 120, so there's no imaginary numbers. And 96 and negative 36 is 60, so it's 120 volts. And if you'll notice, right here is 120 volts. So it's the total voltage. What's what we notice, all right? We're just going to say all imaginary units cancel, and we have 120 volts, and we're done. Kind of interesting. That's it for the last page. See you guys soon.